subscribe, but there will be some people maybe arriving later.
Good.
The group is yours. Go ahead.
Okay. So thank you very much. It's really an honor being here, and many thanks for Esteban and Pablo and other people for arranging this and hosting me. As was said, I'm Matusz. I'm a postdoc at the Leiden Observatory in the Netherlands. And this week I'll be talking about gravitational lensing and strong lensing in particular. So first, strong lensing is my specialty, so I know what I'm talking about most of the time. And also there have been 2 courses on weak lensing before, so I thought we would do something different this year. You can find me in the office 6414, just 1 floor up. If you have any questions, here is my email. And if you want to see my very poorly designed website, you can just type this in. All the slides will go to you after the lecture. And so you have an idea where I come from. I come from a small town called Poprad in Slovakia. It does have some pretty decent mountains. So I was basically born in a place that looked like this. Then after I finished high school, I moved to Bratislava, which is the capital, which has some mountains, but much smaller ones. Then I moved to St. Andrews in Scotland for 4 years to do my studies there. Here is the university on a 1 day per year where there is some sunshine. And all this time I was doing physics, and then in summer of 2012, I went to Waterloo in Canada on a summer internship to the Perimeter Institute, which is definitely the fanciest building I ever worked in. And this is the first time I started working on an astronomy project. And so I went back to the UK after 4 months, and I did my master's thesis in astronomy already. Then I moved to Munich in 2013 to do a PhD. This is again Munich, and there are some mountains, but very far away. And I did my PhD with these 2 people. I can't see them not very well, but this is Simona Veggetti. This is Simon White. You might have heard of the Navarro-Frank White profile. And my thesis was on strong gravitational lensing with millimeter wave interferometers, such as ALMA. And to explain briefly what I did, I looked into how you can go from, this is an image made with ALMA of an Einstein ring in molecular gas, and how from this Einstein ring you can actually reconstruct how does the galaxy look like. So this is the big disky galaxy with lots of gas in it. Okay, you can't see that much detail. And then this is the velocity field, and hola, you can do the velocity field reconstruction as well. And so I got my PhD in 2017, and did the last part of the journey, which is moving a bit further away from Leiden, which is super flat, no mountains at all. This is an observatory, which is not a building I work in. We have a much uglier one. I'm working with Jackie Hodge in monitoring high-redshift galaxies, mostly with ALMA. Here are some results from our recent papers or papers in preparation. So we do both non-lensed galaxies, and I'm doing some strong lensing still. And so I'm happy to be in Medellin, where there are finally some mountains again, and actually very intimidating ones. I'm very excited. Last bit of trivia, I have 2 rabbits that will be featured in these lectures, so my apologies for that in advance. And I'll now get to show some science. So maybe you can't see that super well from the back, but this is a cluster of galaxies. And so all of these big things here are massive galaxies, elliptical. They don't seem to have any disks, as far as you can say. This super bright thing is a foreground star. You can see it from this cross. And then there are a few very unusual things in this image. There is this snake-like thing spread over here. Perfect, thank you. there's this massive snake-like thing spread around here. There is like these two, if you can see these two bluish things kind of connected together. There's some bluish thing going like this, bluish thing going like this, and you might see a few more of them. There are some very fine streaks here. And this is actually a strong gravitational lens. Clusters are very good at doing this. And what is happening here, there's a background galaxy, actually many of them. But this is a very interesting one. It's called the cosmic snake. And you'll see it later on. It's been magnified by and distorted into this massive arc. And this allows us to, it's a very weird shape in the sky, but if you do proper analysis, you learn a lot both about the background galaxy and about the cluster of galaxies in front as well. These are clusters. Clusters are complicated. Single galaxies are much better. So this is a cosmic horseshoe, and it looks marginally better on my screen. You see there is this big bluish thing spread around here, almost like a horseshoe. And why is it dying? Did it get dimmer?
It did.
Okay. Anyway, I'll try to move to bright slides. So there's this big thing around here, which is almost a perfect ring, the so-called Einstein ring. And this is a case where a single galaxy in the front, this big elliptical that you can't see anymore, lenses a background blue galaxy, and it's a much simpler case to analyze. So I'll just briefly go over some details. Okay, this works marginally better. So today, I'll be doing an introduction with loads of pictures, which is mostly the history of strong gravitational lensing. And I'll go over some lensing theory, looking at the simple case where when the galaxy or the object that is doing the lensing is a single point, such as a star or a black hole. Tomorrow is going to be the hardest day, unfortunately, so we will do lensing theory with realistic galaxies. So this is where the suffering will happen, and then it gets better, because then we are back to loads of images and doing some science. We'll talk how we can use strong lensing as looking glass to magnify background galaxies, studying them in detail, but also learn something about the foreground galaxies. On day 4, we'll be talking about how we can find gravitational lenses. It's not that you look at the sky and they are there. They are very rare, and we need to get very sophisticated about how we look for them. And on the day 5, I'll talk how gravitational lenses connect to the big questions in the universe. For example, the expansion rate of the universe, which can be measured using gravitational lenses, or trying to learn something about the dark matter. More organizational stuff. So mornings will be mostly lectures and some online quizzes. I'll be using Kahoot, so I'll send a link around in a second. In the afternoons, there will be some exercises and room for more questions. Except for today, we are having a lecture in the afternoon. I'll be releasing preliminary slides of my lectures always a day in advance. These are still incomplete. They'll be made available on this address. I'll send it around as well. And then full slides will be posted after each lectures. This allows me to have some surprises for you, and also to correct myself if I do something horribly wrong during the lecture. Friday afternoon is going to be different. So we'll try to do some unusual exercises. And this was written when we thought we were connecting to Mexico. I made a list of about 10 to 15 papers on different gravitational lenses. And the idea would be that you would split into few groups. Each group maybe of 3-4 people selects one paper. You let me know which paper is selected. And then on Friday afternoon, you'll do a short presentation describing some basic things about the paper you read. You don't have, not all of you have to speak. You can choose one speaker per group, and the questions are very basic, which is, what is the paper trying to answer? Which lens is it looking at? However, what observations is it using? Is it radio observations, Hubble Space Telescopes? How was this lens found in the first place? And if the lens was modeled, how did they do that? And this is going back to the topics we'll cover on over the following 5 days. And this might be a good way for you to try to synthesize that a bit. This is the general schedule we'll have. So from 9 to 10, I'm in the office. You can talk to me, but whether you have questions about the course or something else. Then there are the lectures here, except this one has moved here. From 2 to 4, we'll have exercises in this room. And from 4 to 5, I'm doing office hours again, so please come and talk to me. Also, if you have questions, drop me an email. Everything is possible here. Just to reiterate, there will be a course repository with all the lectures and the reading list on this address. I'll send it after this lecture. And if you have questions, please raise your hands, ask me. I might be explaining things in a complicated way sometimes, or I might be missing some obvious points. If you want to, there is also an online tool. There's the web address here. I made a copy here. I guess you can't read it very well. So this is a feature called Padlet that basically allows you to post questions online. You can do it during lectures, you can do it afterwards. I'll try to check it every now and then. But this is also good if you have questions outside of the class. And of course, this thing is most likely going to fall apart in terms of organization within a few days, but let's try our best for here. Then, before we go further, I would like to give... No problem. Please take your seats.
Thank you.
Just to summarize for those who came here, there is all the materials for the course will be posted at this address. I'll send it around after this lecture. So, there's also, I'm using an online interface. So if you have any questions, raise your hand, ask, or you can post the message on this address. It's also repeated on the whiteboard. During the lecture or after the lecture, I'll try to read them all and answer to you. So I would like to pay some credits before I start, and I couldn't come up with this material myself, especially not the theory part. So I'm following a textbook or a paper by Narayan and Bartman from 1995. You'll have a link in the reading list. I used some additional sources, the well-known SAS-FE lectures, which are more PhD level, and Massimo Meneghetti's lectures from Heidelberg. I'm also really indebted to people who taught here before, Kun Kauken and Arun, who helped design the exercises we'll be doing. I also try to provide few key papers on each topic we'll discuss. And if there are any mistakes in the following slides, or if I mess something up, it's completely my own fault. Okay, I'll now try to invert this, because now I want to know something about you. And this is a slide I'm missing. So if you can go to, do you know Kahoot? So if you can, for those of you who don't know, go to kahoot.it, and I'll post a link shortly. So which area of astronomy are you most interested in? And I give you couple answers: exoplanets or solar systems. So either planets very far away, or sun, or our own planets or asteroids. Stars, their chemistry, how they evolve, what they produce. Galaxies, both their stars and gas and dark matter. Or do you prefer doing hardcore cosmology, expansion of the universe, inflation? Oh, cool. There's a heavy preference for cosmology in this course. I'll try not to disappoint. Okay, then split between exoplanets and galaxies. Nice. And I'll go to the next, which is the second one and the last one for this part. Sorry, this takes some time. So, which of these telescopes is your favorite one? There is Hubble Space Telescope making amazing high-resolution images. Kepler, that has been amazing for hunting planets. Arecibo, if you don't know it, it's this massive dish at Puerto Rico. Or ALMA, the big interferometer at millimeter waves in Chile. I think Arecibo is a real loser here. Okay, it's Hubble, ALMA, Kepler. Good, thank you very much. This gives me some input. Thanks for playing along. And I'll try to go back to the lectures once this allows me to. Okay. So back to the lensing, and again, thanks for getting to know a bit. This is another gravitational lens I wanted to show you, and we'll see it a lot during this class. And I guess the projector doesn't like black background. So, moving on, it will come again, or I'll talk about it. It's RxJ1131, and what you can see here are these 4 very bright pinkish images that you can't see anymore, and which are 4 images of a quasar in a background galaxy. There's this amazing Einstein arc, and you can also see a foreground galaxy here. And this is a very interesting and complex system, and a very beautiful one, probably the most beautiful lens I know of. And we will revisit it a few times this week. And I'll now try to justify what is lensing good for. So first thing that was ever done with lensing, and the first lensing observation, is the solar eclipse and actually testing general relativity. We can use it to hunt for exoplanets, which has been done, and which I won't talk much about. We can use weak lensing to measure, to relevate galaxies and galactic clusters, and this provides some of the strongest evidence for dark matter. We can look for advanced quasars, and by looking at how these images flicker as the background AGN does something, we can measure the expansion rate of the universe. We can look for we can use deep observations to look for very distant galaxies. This is galaxy redshift 9, found thanks to gravitational lensing. We can try to look for dark matter substructure, and you can see here this tiny galaxy which is associated with this big galaxy splitting the Einstein arc. We can try to look for machos, the massive compact halo objects which were proposed kind of dark matter. We can try to use the magnification here to understand the shape of very distant galaxies and study them in detail. And finally, and this is super strong lensing, we can understand what is happening in the very vicinity of the black holes, which I know nothing about or very little about, and I'll be avoiding for the rest of this week. A brief intro into history. So lensing, we think of it as a very general relativity thing, but it's been around actually for centuries. It works under Newtonian mechanics. So there was this classical lensing period in early 1800s, which got completely forgotten about. Then comes Einstein's theory of relativity, which provided first predictions for lensing, and especially told that lensing in general relativity is different from the one under Newton. The first observation was done in 1919 in the solar eclipse. I'll talk about that in a second. And then it was kind of in a limbo. In 1930s, suddenly Zwicky realized, oh, galaxies can do lensing. And then there was 50 years of waiting until we, for the first time, found a strong gravitational lens. Then it picked up. In the 1990s, we have systematic surveys for lenses. By 2000s, we have dozens of them, found using radio techniques or optical techniques. And it's just picking up. In 2010s, we reached a few hundreds. We did far infrared and millimeter wave observations, which have been very good at finding strong gravitational lenses. So that's roughly where we are now here. And you'll be finishing your university in 2020s, and this is where amazing survey facilities, such as the LSST or the Euclid Space Mission, and in the 2020s maybe SKA in South Africa will come around, giving us 100,000 lenses, and you can do crazy stuff with that. And then in 2030s, we'll get the extremely large telescopes in Chile and Chile, the second one, and probably not Hawaii anymore, which will allow us to do amazing follow-up of these large samples. Just a brief intro, how did this come about? So, as I said, lensing is not something that came with Einstein. It actually works very well with the Newtonian framework. And you can say, oh, hang on, but how does light that doesn't weigh anything respond to gravity in Newtonian model? Because there is no space-time bending. And the trick is that actually in the classical mechanics, you can think of light as a small particle with very little mass, and then you have the gravitational action between, let's say, a sun and a very tiny particle of light. Now we know that photons don't have any mass, but this is 1800s. And actually the first prediction was done sort of independently by these two people, Soldner in Germany and Mitchell and Cavendish in the UK. And it basically says that the deflection angle, when you have a straight light coming in, encounters something heavy, bends a bit, is proportional to the mass of the object that it's encountering and how close it gets, speed of light, factor of 2. And there is a lot of confusion how this all came about, but there is a nice critical review by Wolfsgabot, 2006 and 12, and I'll be sending you the link. And this is where I lost the slide, right? Sorry. Okay, let's go do this. And then comes Albert Einstein, and he develops special relativity first and starts going for the general one. And in 1907, he briefly mentions, yes, the bending of the light, it would be an interesting effect, leaves it hanging. Then he makes a detailed calculation in 1911, alpha equals 2 gm over c square r. Notice something. It's the same as the Newtonian one. But this is the prediction. Some people do calculations and realize this is observable during solar eclipse. So they tried to observe this actually twice, in 1912 and 1914. It doesn't work. Neither time, bad weather, and the war started. And Einstein got super lucky, because in 1915 he realizes he got something wrong in this derivation and corrects himself. So he got very lucky, because if one of these observations was successful, but he had the wrong prediction, this would be a major problem for acceptance of relativity at the time. At the end of the war, the US tried again in 1918, and again, the weather wasn't cooperative. And then it boils down to basically Einstein, this guy over here, and Arthur Eddington, a British astronomer, who after the war decided to use the 1919 eclipse. This is just 1919 eclipse to do this. So the idea is, if the sun is very massive, as the moon blocks the sunshine, you'll see that the starlight that just passes around the sun, the star positions would shift a bit because because the light is attracted towards the sun. You can't see it during daytime, the sun is too bright, but during eclipse, this should be possible. And so there was this eclipse in 1919, and it seemed to be ideal for this type of exercise. It intersected some land, which is good, at Brazil and Africa. It was long. The sun would be completely obscured for 6 to 7 minutes. And the other thing would be that the sun would be passing in front of very bright stars in the Taurus constellation, which makes it, if you have bright stars, it's easy to measure the deflections, easier than if you had very weak stars. So the British sent 2 expeditions to hedge their bets. One to an island called Principe in West Africa, one to Sobral on the coast of Brazil. And I'll just go, long story short, what happened is Principe got pretty bad weather. They managed to take some photographs, but none of them was of high quality. And Sobral expedition had actually 2 telescopes, a 16-inch one. These are solar observations, so the telescopes don't have to be big, and actually there are these weird mirrors in front of them that allow you to track the sun much more efficiently. So this was the main instrument, and then at the last minute there was a proposal from Irish astronomers that they should take a 4-inch telescope as well as a backup option, which worked out very well, because what happened to the main telescope during the eclipse, because of the heat of the sun, the mirrors and the total construction, including the photographic plates, expanded too much because of the high temperature. The 4-inch telescope worked very well. And so here are the published results from 1920. This is the solar corona. This is the shade of the moon. You can't see it here, but there are 2 vertical lines here which indicate 2 bright stars in Taurus. And very recently, ESO and Heidelberg, okay, now you can't see anything here, reanalyzed some of the plates. Now the image quality gets much better with this protuberance here, and there are a few very bright stars highlighted in these plates that were used to measure the angles. Fun fact, this is what we are going to do tomorrow during the exercises. So here's the published paper. I believe this is the Newtonian prediction. This is the prediction by Einstein. This is the best fit to the data. This is how far the star is from the sun, how much is displaced. This is close to the sun, big displacement. Far from the sun, no displacement. And that worked pretty well. Then in 1936, Einstein did some more detailed calculations, but again, back then the idea was only stars would do the lensing. And this experiment continues. It has been done, it started in 1919, and then with each eclipse, people have been trying to do this better. Then they realized radio wavelengths allow you to do to higher precision, and you don't need to have an eclipse. And now with the global VLBI, basically here is the GR prediction, and we are within it to 10 to the power of -4 error. This is a completely different test that is also measuring the GR, this consistent with the GR prediction to a large extent. And so this is lensing by stars, but I'm going to talk about strong lensing, and that had to wait for a long time. To Zwicky, who was a Swedish Swiss astronomer. This is not one of his best pictures, but he was apparently not a pleasant person. And until Zwicky, people thought that galaxies are not actually that heavy. When you measure all the stars in the galaxy, the total mass is not high enough to do strong lensing. And Zwicky was the first person who came up with the idea that for clusters to all together, we need additional mass component, which is dark matter. And then suddenly you multiply your mass of the cluster by a factor of 10 or more, and it can do lensing. So there were 2 seminal papers in 1937, where Zwicky proposed that nebula, which means galaxies, actually can act as gravitational lenses. And then people kept on trying, but it was done with photographic plates, and you didn't really know where to look, so that was tough. And then in 1979, this actually happened using radio astronomy. So people were looking at radio-bright quasars, and most of them are actually at pretty high redshift, even with the 1970s technology. So they might be very good, when you have your foreground lens, they might be a very good background source. And there was a paper by Walsh, I'll just do this, by Walsh, Carson, Wyman, who were identifying a lot of radio sources, especially quasars, and then doing optical follow-up to get their redshifts. And they found these two quasars, so this is low exposure. There are these two objects, A and B, that are quite close together. And when you do much deeper exposure, which was figured out a year later, there's actually a lot of galaxies in between them. And when they took the optical spectra of these two galaxies, this is just raw data, they actually end up looking damn similar. And this is a slightly, well, not so much better, but a spectrum taken a year later where you see the lines identified in both of these quasars. And so they wrote to Nature proposing that either they have two quasars at the same redshift very close to each other, or as a more controversial proposal, they actually have a first gravitational lens where a single quasar is sliced into two images. And that's actually indeed what happens. So here is a Hubble Space Telescope image of this quasar, Q0957. Here is the foreground galaxy. Here are two blue images of the quasar. This is, okay, you can't see what is happening here. But if you go to radio, you see one of them has this amazing high magnification jet from a background AGN. The other image, the image B, is much more compact, so you can't see the detailed structure, not in this image at least. And there is some emission from the foreground lens galaxy. Fun fact, while this was in progress, Walsh, the first author of the paper, made a bet that with a colleague that if he finds a gravitational lens, he wins some money, and he did. So this is a quote with a paper I put in the reading list, if you want to read it, which basically, yeah, you can make money out of gravitational lensing, but he's probably the only person who managed to do that. And since then, the field has advanced a lot. I'll just give you a sample where we are now. We found, as I said, hundreds of lenses. This is a composite image of 60 plus lenses found in SDSS survey, just using one technique from the SLACS team. RxJ1131, we have some now super high resolution images of these galaxies. We have many clusters and groups of galaxies, such as this one that is lensing these nice Einstein arcs. We have something like, okay, you can't see much here, but you see here there are 4 images here, and the bright thing here is a central galaxy. This is Einstein Cross, another famous lens. We did other instruments. At millimeter wave, this is SDP81, observed by ALMA at 0.01 arcsecond resolution. So this exquisite Einstein arc with loads of structure in it. And at the highest resolutions, we have the global VLBI, and this is an image by a friend of mine from her recent paper, which shows this amazing Einstein arcs, razor sharp here. Here is a counter image of this bit. There is another structure down here. So the point of this course is actually going to get us back to the same image I'm showing again and again, RxJ1131. Because this summarizes very well a lot of problems we'll encounter for the next week. So it's obviously a strongly lensed system, big arc, multiple images. It has 4 images of the background quasar, and as we will see tomorrow, for this to happen, your lensing galaxy has to be elliptical in potential or density. It's not a spherical galaxy completely. There's an extended source that creates the Einstein arc, so you can try to map how does the background galaxy look like. if you look very closely, so here is the main lensing galaxy, but there's a bit of blob of light here. There's another, which is a satellite galaxy of the main galaxy, and it basically acts as a substructure of your lens. So the lensing galaxies can be complex things, and lensing will allow us to understand their structure. And finally, these 4 images don't have constant brightness of the background quasar. Quasars vary in intensity because gas falls in, jets go out, and so they vary with time. But if there is a change in the quasar, it doesn't arrive to all of these 4 images at the same time, which we will see again tomorrow. And the difference between and the time delay between something appears in this image and then this image, and this image allows us to measure Hubble constant. So I think this pretty much encapsulates all the challenges we have with strong lensing, but also all the questions we can try to answer with that. And that is my last slide of the introduction. And if you have any questions, maybe ask now. No questions so far? Good. So in that case, I'll drink a bit more water, and we move to the less exciting part of the lecture, which is the theory part. And for that, I would actually like you to pass around some handouts, which we will be referring to repeatedly throughout this week. If you can just pass it through. So I'll try to answer that question, which actually, let me go back to it. So the question is, why is the difference in the form of the gravitational lens in this picture, and why there are 3 points on one side of the lens, and I assume the single pink point on the other side of the lens. Oopa. Here, can I go? Sorry. Okay. So yeah, that's a very good point that we'll see later today and tomorrow. A lens that is elliptical will typically produce 4 bright images, and where these 4 images appear really depends on how does your background source, how is it positioned with respect to the foreground lens. So if I would go a few slides back, here you again have 4 images which are more evenly distributed. They are really like cross boom, boom. And this happens when the source is more directly behind the lens. And as it starts moving to the side, 3 of these images will start moving closer together, which is what we will look into tomorrow in more detail. But basically, the asymmetry of the lens tells you something about where exactly is the background source located with respect to the lens. That's already a very important piece of information when we are trying to understand the systems. Good. If there are no more questions, I'll start moving to the less pleasant part. So today, over the next hour, we will try to go over the mathematics of the lensing theory, but I'll try to let me explain this in more detail on more slide. Today I'll focus on the simplest case, where our lens is really a point-like mass, think a black hole, or actually a single star, like our sun in the solar eclipse experiments, or stars that we see through microlensing, or exoplanets. These all can be point-like lenses, and point-like lens has a lot of nice advantages. It's a singularity, it doesn't have much angular extent, and it's very easy to handle mathematically. But I'll overview some concepts we'll cover today. We'll talk about the deflection angle because that's the main thing that happens during gravitational lensing. How do you force a ray of light that's going straight encountering something very heavy? How much does it bend? And it depends on the distance to the source and its mass. I'll introduce something that's called the critical mass density. I'll talk about lensing equation, which is how we can do really calculate the deflection angles for a given lens. I'll talk about the Einstein radius, which is something we'll hear about a lot the next week. I'll explain magnification, which is really the key concept for gravitational lensing and its key strength. Magnification means that the sources appear larger and thus brighter when they undergo strong gravitational lensing, and this is really one of the reasons why we are doing this. And I'll talk about the image parity. There is a number of assumptions that go into this, and we are working in the framework of general relativity. I'll be honest, I've been working with strong lensing for 6 years now. I never used a bit of general relativity, and I'll keep it the same way for you. There is a single equation at the beginning from which we can derive the rest. We are using Friedman, Lemaitre, Riemann. Good. Robertson. Thanks, metric. See, I haven't done this in ages. So we assume that the space is isotropic and homogeneous, except for where we have the lens. And this is a pretty important thing, because in many realistic cases, there is a lens here, there is a source over here, but there might be some stuff along the line of sight. We assume that the time can be separated from space, so we are not doing vicinity of black holes, even Horizon Telescope. We say that the distance between the source to the lens and from the lens to the observer, these distances are much larger than the actual size of the lens, which is, again, we basically make sure that we are not doing some extreme cases here. Small angles everywhere, so we can use some nice approximations. Nothing moves too much. So in our case, source versus lens is stationary. This, again, is not necessarily the case in reality. And for most of the derivations, we assume ray optics apply. I'll highlight a few cases where things would start falling apart if you push the ray optics approximation, but for us, light, you can treat it as particles, and it goes in a straight line. So this is hopefully a familiar thing. This is a block of glass, let's say. There's a ray coming straight in. It encounters a denser medium, bends, gets out of the denser medium, bends again. And you can think about the gravitational potential a bit the same way. There is a vacuum here. The light doesn't care about anything. Encounters something massive, reacts to the mass it's encountering, and then again leaves the mass, but now with a perturbed path. This is how it looks like in lensing situations. So you have some background galaxy. Now you have a lensing galaxy. Here is a galaxy cluster, which adds a lot of complication. The thing with the galaxy cluster, it doesn't have a uniform optical index, as you would say, and that I will show on the next couple slides. And this means that the light from galaxy can actually take more than one light path. So here, single light path. Here, we will have multiple potential pathways. And then some of them actually intersect the Earth, where you can observe them. All of them go completely away from us. Okay, and now here's the figure I'll be referring to a lot for the next 2 days. So this is a Bayesian lensing scheme that I did for my PhD thesis. Here is a lens. Notice it's pretty narrow, and in fact, for most of what we do, we expect that the lens is infinitely thin. Again, these distances are massive. Here is the observer, and here is the background source. So if there was no light, if you would forget about the lens completely, the light from the source that we would see would follow this path, the dashed line. Now there is a lens here, so what means that the light that would go here gets deflected away from us, and instead another path of light, which would go normally up here and miss us completely, gets bent and hits us again. But when we look as an observer from here, what you would see, now you see that the light is coming from this direction, so your source seems to be over here. And we'll call this is a source, this is an image, and this is basically the deflection angle by which the ray is bent. So you start over here, then something happens, you move down here. And this is alpha hat angle. Alpha hat is difficult to pronounce, but this is what is used in many of the papers and on the reading list. So for consistency, we keep this. And then we do the general relativity part, which is this thing. So, okay. So if you have, okay, you won't see the red. So if you take the example we saw before, where we have a block of glass, so this is the optics you are normally used to doing from high school or university, you have a single optical index n. And we would like to use the same, and we know how a ray behaves when it enters here, bends, goes out again. And we would like to use the same notation for the gravitational field. So we need to link the optical index n to the potential, ideally. And this is actually done very simply through this very first equation. The derivation is not simple. It's in Massimo Meneghetti's lectures, which I will share around if you want to see the details of how this is achieved. Remember this. From now on, forget about the general relativity for this bit. And now I'll just try to write that equation down here. So that's n equals 1 minus 2 over c squared, where c is the speed of light and your gravitational potential. And that's really the Newtonian thing you have. And then we have second issue here, which is that the block of glass that I need to draw again has the same optical index throughout the entire material. Now, if you have your star, let's talk about stars for a second, you know its gravitational potential is different here, and it's different here, and it's different here because here the gravitational force is small, larger, very large. So your optical index is not the same everywhere. It's going to change. As you go closer and closer to the lens, your optical index will get higher and higher. So we want to know, how does the light react to this? If this was a single block of glass with n equals constant, you know, the light goes in, you take the Snell's law or the 1 over n sine theta thing, you calculate your deflection angle, then the light goes straight through the entire block, then it exits again, and I don't know how to draw this anymore. But here what we have is that instead, our optical index is not constant. If you think of an optical block of this galaxy, up to here you don't care about the galaxy, then you come here, and you start feeling its pull. So instead of going straight, you start bending, and bending more, and bending more, and bending more, and as you get closer to it, the more you bend, and then at some point you exit the block completely. So what I wanted to say is this is motivation for the second part, that it's non-intuitive, which is how do we respond, how does the deflection angle depend on this refractive index, and it's simple, it's the gradient of the refractive index in the perpendicular direction. We don't care, our lenses are mostly infinitely thin in this case. So that would be alpha hat equals minus, this means it's in the perpendicular direction, so don't care about the third dimension, and your phi, xy, zy, dz. Where if you would remember the scheme from the here, x is the perpendicular dimension vector, so we are doing cylindrical coordinates here. This is still a two-dimensional vector, and z runs along this axis. And then you can, gradient looks a bit scary, but you can basically do this a partial derivative with respect to this vertical vector x, perpendicular vector x, because we are doing only perpendicular dimension. And now you can safely substitute for this expression from here, and you have this alpha equals 2 over c squared, and an integral of a partial derivative of phi with respect to x along the, dl is the z-axis, my apologies. Okay, we have a formula now, and we actually do know gravitational potentials for a lot of things, such as a point mass. So we can do this. I'll try to do a simpler demonstration here. So you take, if you take your gravitational potential in the cylindrical coordinates, so in 3D, you would have only the radius, and then you have a potential for a point mass is minus gm over r. Then you need to decompose the radius r into two components, z and x, so it's square root of x squared plus z squared. We can do derivatives. So if you take a partial derivative of this with respect to x, you get gm over x squared plus s squared to the power of 3.5. I hope I don't have to derive that. And then there is this x here, and also the direction matters. So now gradient has a direction. Here the direction follows the x vector, which means you'll be pointing towards the mass here. And then you need to do the integration down here, which I couldn't do by hand. So I used the free version of Wolfram Alpha. Wolfram Alpha, you can use it yourself. And what you get is very simple, something as 4gm over c squared x. And if you remember something a bit, this is exactly the result that Einstein got. Now there is something very mean that happens here. So this is pretty well defined. If you would take your paper here, so this is defined for all the vectors, all the sizes of vector x, except when x equals 0, where your source is right directly the lens, right behind the lens. So what is happening there? And this is just the warning. This is where our approximations fail. Because what we have now, so first we have a point-like mass. So if the x is 0, the light goes like this, and then hits our star. So in principle, in reality, you can say, okay, this is blocked. But also what happens here, if you would look at the gravitational potential, here is the singularity. And you can't do this with ray optics anymore. This behavior, if you wanted to do it properly, you need to go to wave optics and use all the diffraction patterns that will start forming around the lensing object. So this is what event horizon people might be doing. We are staying safely away from that. Okay. So, okay, I didn't have to sketch that. So basically the point is, if you go straight here, and you have only a point-like mass, you hit a singularity, and all your approximations of weak, of ray optics, and that the potential is weak, and that the angles, especially deflection angle, are small, fall apart, and you are stuck. So that was done all in 3D. Remember, we still had this z-square factor that tells you about what happens along the line of sight. Normally, we don't care about this. Like, if you take this image, and if this was a galaxy, so your typical galaxy maybe is few kiloparsec in size. This might be easily 1,000 megaparsecs. This might be easily 10,000 megaparsecs. You don't care really what happens as you go inside and out. For most, especially not for the deflection. So we want to go from a 3D case into a 2D case, because all those things get easier when you don't have to do three-dimensional integrals. And that means going from volume density into the surface density. And again, take your general potential we had before. So it's 2 over c squared, and you have this gmx over x squared plus z squared. But what you can do as you go across the lens, you can just integrate along the z dimension and get your surface density, which is what happens here. So your surface density is just the integral of the volume density along the z dimension. So if you would think of it, now we have a big lens here. What do you do? Your surface density, you have some volume density at this impact parameter x. Oh God. And that might change, but you basically only care what happens when you integrate it along the line of sight. And this gives you your surface density. And it's an easy one-dimensional integral, and it's often fairly symmetric. And when you would work it through and you need to care about the dimension of about where the things are still pointing, so you replace x by this type of thing, where your integral now runs over x prime. I'll try to do quiz now, if that's okay, because I think this is where a lot of people get lost. So I'll just try to explain again conceptually what this last part does before we move ahead. So if you consider some array that intersects the lens at position x prime, what is happening, what your deflection angle depends on, is basically you need to integrate through the entire extent of the lens and consider basically what is the surface density in any point of the lens, which is given by this x prime parameter. And then it's basically 1 over distance squared between your point of interest and each point of your lens. So what I will do now, before I launch the Kahoot, as I learned from my mistake, is we have this is a very idealized lens. The lens is composed of 5 chunks, each of the same mass and surface density. This is the entire extent of the lens. And so we have 3 different sources here. There's a source A, where the ray goes like this. Here is a source B, which goes through the middle of the lens. Here is source C, which goes through the bottom of the lens. And if I try to do the Kahoot thing again and not cancel everyone. So now you take this lens, composed of these 5 packages, ray going through the top, through the bottom, through the middle, and through the bottom. Which way will the rays bend? Will it be, the option A is basically down, 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 then it's down, down, up, down, up, up, and you can fill it in yourselves. And if in doubt, you can try to use this equation if you can see it. Well done. That was very successful, so thank you. So if I go back to the slide, just to explain. so if you think of this, well, this equation, consider, so here in this case the surface density is the same everywhere across the lens. Let's start with the ray B because that's going through the center of the lens. So the mass to the top of it is the same as the mass to the bottom of it, and also the distances are the same. It's a perfectly symmetric cause. Now we also don't have it's not a point mass anymore, so there is no singularity that would screw things up in the middle. So this just goes straight through the lens. Now, when you consider image A, most of the mass of the lens, so basically, most of the mass of the lens is to the bottom. Okay, that might not, it also depends on how it's distributed, but basically the contribution of this part on top of it and this bit to the bottom of it would cancel out in this, because this would basically just reverse the sign. And then you have all these things over here, which has a lot of mass, and all this offset to only one side of this ray. So this one will bend down, and the one that goes for the bottom has the same thing. Basically, what is down? What is it? It's this part of the lens is pulling it down. So is this part is pulling it up. They cancel out. All of this is pulling it upwards. So we have a question. It's an answer D indeed. So now we will do it. Okay, there is a lot of. Let me do this. Okay, so far so good. So I'll now make this a bit different. Oh, no. No points awarded here. So now we take the same lens, and now we extend it to the infinity. So these blocks of matter go all the way down to the infinity, all the way to the top to infinity. How will the rays go now? Will they go, you read the options. So now it's basically a uniform sheet of mass extending across the entire universe. How will the light bend? Excellent. Just to explain now, when we extended everything, for each ray, it sees exactly the same situation to the top and to the bottom, to the top and to the bottom, to the top and to the bottom, and they just go straight. So a reaction of the light, or its bending to a sheet of uniform mass, is that there is no bending. And we'll actually encounter this later this week. This is called the mass sheet degeneracy, that you can just add uniform amount of mass across your entire lens and nothing is going to change with it to the first order. So now, having moved over that, I want you to use your sheets again. And I'll use this. So what we would like to do now, so now we know a prescription for this deflection angle for a given approach to the lens. But this is not really what we see. We don't know, when we are down here, we don't really know, can't calculate the bending angle. We might have some idea of what is this approach to the lens because we see the projection. But what we would like to do is, if we see a light coming to us like this, so we see an image over here. We want to know where it came from. So it's a kind of a way we try to invert this process. Instead of going from the source to the observer, what we want to do is go from the observer. We know the ray of light we detect. We probably know something about the lens. How do we find the source? So this is where some trigonometry will come in handy. But it's all small angle approximations. So if you would take the distance, between the source and the image, and you look how it, Okay, let me make sure this is. So the distance between the source and the image is related to the deflection angle. It's basically the deflection angle times the distance between the source and the lens, which I denoted DLS, and you see it up here. It's just a small angle approximation. But also, you can extend this much further, and it's also the distance between the source and the image is basically the distance between the observer and the source, the ds, times this additional angle alpha, which we call the reduced deflection angle. So just find this on your papers, take your time, look at the difference between the source and the image, and then check for yourself that this indeed holds. To explain again, these are small angle approximations, so we don't really need to care about sines, cosines, and all these complicated things. So it's just a simple approximation that, the distance subtended by the angle is the distance to the whatever we are looking at and the angle itself. And then we can very simply basically look at this part of the equation and express this angle alpha x as a function of the alpha hat and these two distances. And I hope I kept my DLS and DS on the right side of the fraction. And then you can consider something else in your image. So the distance between the optical axis and the original source position is just the distance to the source times this angle beta you can see in your images. So that's the distance between 0 and the source. I'll try to move it up here. Here is as an observer. Here is your source position. And here is the angle beta under which you view the source. And so this is your distance ds. And so S vector equals just ds times beta. And then you have this image up here again. And I believe what we just derived is that the distance between the image and the source, so I'll do it in absolute values, or whatever. Image minus source equals equals ds times this new angle alpha. So you can combine these together as a vectors where you try to relate the source position to the image position. And your image position is basically, okay, now we have also the angle theta. So your image position is now basically ds times theta. But it's also just source position plus this image position plus minus source position, which is ds beta plus ds times alpha, which is exactly this equation. And now all we are after is basically knowing your angle theta, which is so if you know your angle theta, which is under which angle does the light come from, you want to know the angle beta, which is where you would see the source if it wasn't perturbed. And it's just simply this. It's the angle theta minus alpha. Just divide this through by ds altogether.
Sorry.
Yes?
So our point of reference all this time is like the source of the line, which connects
Yes.
It connects the observer with the center of the lens.
Yes.
That's our point of reference, like the center of the lensing object.
That's a good point. Yes, that's the line we will use, because then everything else is symmetric around the line between you and the lens. So I'll move one slide further, which is the same equation still. And I wouldn't put this to the audience. So if you look at the equation, there's two questions you might generally have. Is this linear in general? And is it going to have a single solution? Or is it going to have multiple solutions? And in general, so beta depends directly on theta, but alpha theta can be a really nasty thing. So no one guarantees you that this equation is going to be linear. And also, it's not guaranteed that you have more than one solution, that you have only one solution to this equation. 2 or 3 or a lot of solutions to these equations are possible. And we saw before that we had these lines where we have 1, 2, 3, 4 images. These are actually solutions to some sort of a lensing equation. Now, throughout all these things, there is one complication, and that's about these 3 distances. So you have the distance to the lens, distance between the lens and the source, and distance to the source. So I made this nice image where they seem to add up nicely, but is this generally so? And the point is, well, is your space flat and non-expanding or not? If it's flat and non-expanding, which is basically what happens in our galaxy when you consider lensing by stars in our galaxies, lensing by the sun, lensing by something maybe in large Magellanic Clouds or further, this actually adds up. So within the galaxy, we can do, yes, the distance between us and the lens plus the distance between the lens and the source is the distance to the source. In the extragalactic sense, where things are in expanding universe, often at high redshift, this is not generally the case. And I'll explain that here. So what these distances actually are, they are called the so-called angular diameter distances, which allow us to do all this nice distance times angle equals physical distance over here. But they are not really additive. So what is a plot here is a plot of the angular diameter distance in megaparsecs, depending on the redshift. So, we are at redshift 0, and as we go to higher redshifts, we go back in time and looking at more distant galaxies. And so at low redshift, sure, this goes up pretty nicely. I wouldn't say linearly with redshift, but then at some point around redshift 1, there is a turnover. And then it actually slowly goes down to very high redshifts, and then things get complicated again. So normally, I don't try to solve this by hand. There are online tools. I'll send some links around for a given redshift to get the angular diameter distance. And this is really the effect of the fact that the universe is expanding, and here you see two slightly different cosmologies. And it really depends on your Hubble constant and other parameters you have. One thing that makes it simple for us at the moment is that the universe seems to be at least flat. So it's really the expansion of the universe you have to take care of, but nothing much worse than that. There is another interesting thing with this plot when you think about. So here we have here we are as an observer, and we are looking at some galaxy at very high redshift, which is our source. And now even forget about lensing for a bit. So we have some angle here, alpha, and the physical distance here in whatever kiloparsecs is going to be ds times alpha. Now your ds of course, increases rapidly to around redshift 1, but then stays the same, sort of the same, and actually slowly goes down. And what this means is if you have a telescope of a fixed resolution, for example, Hubble Space Telescope, so your resolution is, I don't know, 50 milliarc seconds, the physical distance here in kiloparsecs, so how, if you take a galaxy here, how much resolution are you going to have as a function of redshift in physical units? Actually gets better as you go to more and more distant galaxies. Or, I mean, that's marginal, but stays the same or gets marginally better. So you don't lose the resolution when we look at very high redshift galaxies. The thing that really kills us here is that this is the angular diameter distance, but your light gets fainter with redshift very rapidly. So the galaxies might be of the same size, but they are orders of magnitude fainter when you go from redshift 1 to redshift 4. Sorry about that. Okay. I'll ask if there are any questions at this point before we move on to solving the lensing equation. Okay, yes?
Will the equation beta of the bending angle have infinite solutions?
Yes.
What cases?
The one that you will see in 3 slides. Yes, because what I'm doing, I'll wait 3 slides. I was going to explain something, but it's basically skipping 3 slides ahead. But yes, there will be, in principle, infinite solutions. But again, there is an issue. The ray optics approximation starts failing in these cases. Okay. So now we'll do some derivations. I'll try to do this slides board, and then maybe you'll repeat some of that. So we'll now try to see how many solutions we get for a lensing equation. And we take the simplest thing we can think of, but not point-like mass yet. We just assume we have a circularly symmetric profile. A lot of things, if you think of a galaxy, you can approximate it as a circularly symmetric thing for now. So you have these 2 equations. You have the lensing equation, and you have the equation for the deflection angle, which for the deflection angle and its angle alpha that is related to just by ratio of 2 distances. So let's mesh these 2 together. So now you substitute for alpha into this equation, you get theta minus dLs over ds alpha. And then you can use the Einstein result, but I'll just try to strengthen that again. So you have your alpha is basically the 4g over c square integrated over this ugly thing. But if you are in a circular symmetry, it's basically 4gm over c square, your mass enclosed within some radius, divided by that radius. 4gm c square over x square. And if you consider your handouts again, this x is just theta times dl. This is nothing surprising. It's as with the gravitational potential, the strength of the gravity depends on the mass enclosed in case you are in the spherically symmetric case or circularly symmetric case. So this becomes 4g with an angle of theta over c square dl theta. Just pure substitution here, and I just cancel dependence on dl because we don't care about it in here. And then we get something like this. So beta equals this thing over here. Now this is not necessarily simple. There's some dependent, well, there's beta here, there's theta here. Beta can have all sorts of values. But consider the source right behind the lens. So set beta equals 0. That means you say my image is right behind the center of the lens. So this is 0. And then we have basically this thing equals 0. And like this is something we can solve. Like this is theta up here, theta down here equals 0. That's as good as a quadratic equation. So you can try to multiply, basically multiply through by theta, and you assume that theta is not 0, because that would create some problems here. You just have a quadratic equation. And actually the simple one is just theta squared equals one chunk of thing where this is mass enclosed. And so, we can take the square root of that, and you get the plus minus some value in here, which only depends on the mass enclosed. Notice what happened here. We suddenly got two solutions. There is a positive theta and negative theta. And did I cancel my lens? Yes, I did. And what that means, basically, so now our source is over here. Here is our lens. Here is the observer. There are two possible solutions, plus theta, minus theta. And this means there are two different paths, up and down. And this is again because we are in a circular symmetric case. If you would, you expect the same solution up here and down here, because if you would flip it, by the nature of symmetry, expect the same solution. Does that make sense? And now, this is going to back to your question, and I'll skip a slide here. So this is a cylindrical coordinate system, right? There is one axis here, but actually what happens here, this is a two-dimensional case. So what you can do, you can not only flip these things, you can rotate them by any angle you want. You can basically take this and start rotating it around. So you have a solution here, rotate it a bit, solution here, solution here, solution here, solution here. As you rotate it, and basically if you do this, because it's circular symmetric case, you get a full ring. You have infinite amount of solutions, as far as you can say. And that's the Einstein ring, so I'll skip a few slides. This is what you will get out. Here is the position of your source, right behind the center of the lens. And you have this nice ring with some characteristic radius. And now we go back 2 slides where I explain 2 quantities that we want to have. So we have these 2 characteristic solutions. Now 2 things happen. Gives us some characteristic radius. But before that, see, this is what we have. We are doing gravity, and this is very common for gravitational problems with this symmetry. We are only sensitive to the mass enclosed. We don't care at all how is this mass distributed as long as it's circular symmetric. You don't care if this is, a point mass. In fact, if this is a uniform distribution of mass, if this has some profile there is a lot of mass in the center and then it tapers off. So a handy thing to have is that say, let's pretend the mass distribution inside of this radius is constant. Not everywhere. That's the mass sheet, which doesn't have any deflection, as we saw in the quiz. No, just inside this radius. And this gives you, basically, if you consider this that mass enclosed is just the size of your aperture you are considering, and some surface density here. This gives you the so-called critical surface density, which is a typical density at which strong lensing will happen. We'll explain this more tomorrow. And then there is the characteristic radius of the ring, because we have these two solutions in theta coming from this, and this is the Einstein radius. This is how we call it, Einstein radius, which is if you have a perfect alignment of a circular symmetric lens and a source, you will get a ring in the sky, just like here, with a characteristic radius. And I'll just show that this actually happens. So this is the lens I was showing before, and sure, it's not perfectly circular, that's why, and the source is not point source, but before the projector dims down again, there is this pretty nice ring going almost all the way around. And is this, okay, this does not help. This is the same thing with RxJ1131, and I'll skip to a bright slide, so it warms up. And then back again. So what you see here is that the Einstein radius is related to only few things. It's related to the distances, to the lens, to the source, and between the lens and the source, which is basically get these from redshifts. No, you don't, sorry. And the mass of the lens. So if you want to use Einstein, so you would think, okay, I can calculate Einstein, I can get all these parameters, redshifts, mass, and calculate Einstein radius, but in fact what happens is that we might know the distances because we assume cosmology we get the redshifts, but you measure the Einstein radius, like in this ring it would be roughly its radius, and this gives you the mass enclosed. You know the free distances from redshifts, you know this is you take a spectrum, you know where this is coming from, where the redshift, where is this coming from? We are at redshift 0, obviously. You measure the Einstein radius, this is just the separation of the ring, and you get your mass enclosed. And this is how we made galaxies. The second thing that lensing is useful, not only testing general relativity, we can evade galaxies from it. And this would have a much fuller Einstein ring, but the projector is dying. Now I'll have a question for you. So if I don't close the Kahoot again. Okay, that was maybe too early. But think about this. So a case in point of this circular symmetric lens is a point mass lens. Now it's straight in the center of this axis of symmetry, otherwise there is nothing. How many, depending on the position of the source, how many images will it form? Oops. How do I go back? Okay, my apologies. So I'll just reiterate the question, which is we have been so far, so what we just derived is this Einstein radius and a ring-like consideration for a point-like lens. How many for a circular symmetric lens, if our lens is point-like, how many solutions will we get for it? Depending on the position of the source. So right now we looked at, source is always directly behind the lens. If it's not directly behind the lens, how many solutions will we realistically get? Okay. So it's very quick. 1 or 2, always 2, 2 or 3, 1, 2 or 3. Well done. It will be always 2, and I'll show that in the next slide. Okay. So we just did the Einstein radius thing. And so now we consider again the lensing equation. So you have theta minus dls over ds alpha. And now you combine this together. you have some mass enclosed, and this is the same for whichever radius you picked, because the mass is something if theta equals 0, and then there is no contribution from anything else. So now we don't assume beta is 0. We leave it in the equation, and now we get a full quadratic equation. So just like this. And once I remembered how to solve quadratic equations, you get the following result for the formula, which is like 1/2 beta plus minus this thing under the square root. And if you remember a bit, well, it was really shortly. If you look at this expression, it's just what's inside of here. So you can simplify it as this. Now the number of solutions to this equation, these real solutions, depends on the thing in the under the square root. This is always positive. This is always positive. There is a plus sign here. So there is always going to be 2 real solutions to that. In theory, definitely not in real life. So in theory, the answer, there are 2 solutions to this, is correct. But think about it realistically in the sky. Let's say I have my source over here. I have my lens way over here. It's a point-like lens, it's a star. Of course, in the real life, the source that's so far away from your lens is not going to have second image somewhere over here. And what is happening here is, again, our approximations are breaking down. All this formalism works only on your sheets, works only because we're using small angle approximation. Put your source too far away from the lens, put it on the other end of the sky, and this completely breaks down. We are left with realistically single solution, which is source that doesn't care about the star so far away from it. I believe I have 5 or 7 minutes, Esteban. Speaking of, so we saw a few slides ago this nice Einstein ring, and you can measure Einstein radius from that. That's easy, because you have a ring might have a pretty well-defined radius, but what do you do if you don't have a ring? You just have 2 images, and you still want to weight your lens. I mean, for rings, you have to have perfect alignment between the source and the lens. That's very rare, but you still want to weight galaxies. So consider this expression a bit. So when you consider this expression a bit, and just to explain what kind of lenses I'm talking about, something like this. So this is a very well-studied lens, seen in 2 different images. This is a combination of different colors. This is, I think, this is a near-infrared image. You see these 2 nice images and a lens in the middle. We want to weight the lens. So you know the distance of one of these 2 images. The shorter one is beta minus this thing. The larger distance is beta plus the thing in the square root. So you have these 2 distances. And if you take the distance between these 2 images, you just basically subtract these 2, I hope. And you can Taylor expand that. So you get something like this. And when you Taylor expand, the first term is 2 Einstein radii, and then beta square plus some higher order correction, and typically your beta over Einstein radius is pretty small. So basically, just knowing the distance between these 2 sources gives you twice the Einstein radius, and as we saw before, Einstein radius gives you mass, provided you know the redshifts. So even with only 2 images of a single lens, we can measure how heavy is the lensing galaxy. Good. I'll now cover the last topic of today, which is something you can see in these two images. These two and these two, I mean, it's the same lens, okay. They are not equally bright. This one is clearly brighter than this one. This one is, okay, brighter than this one. I think that's probably still, we can see that. So we know so far we've been only talking about the positions in the images, but there is actually something happening to their brightness as well. And the something happening to their brightness is the big thing why we do gravitational lensing, because it makes background sources very, very bright. So I'll talk now about magnification. Magnification tells you how bright the images are, and there is one thing I omitted saying before, so my apologies for that. So let me explain. Lensing, as any other non-active optical system, preserves surface brightness. If I have an image like this, okay, is this brighter? If I have a source like this, and I do to it whatever I want, whether using gravitational lensing or normal optics, you take your normal lens, you make it much bright, much bigger. But when you would consider a unit angle here, the unit solid angle, you can't really make the brightness here is the surface brightness here is the same as the surface brightness here, and this is because you're not pumping the radiation in any way, and also because there is no loss. So basically, if your light goes from here to here, you are not putting more photons into it. You're also not putting less photons into it. Okay, later this week. But definitely pumping doesn't happen. So the only thing how your image gets brighter in gravitational lensing, so you have a source, it is gravitationally lensed. It's because it got bigger. And for this, again, point-like approximation doesn't work very well because point to a point doesn't necessarily work particularly well. But what you can do, why did I delete this? So you have one source over here, one source over here. What do you integrate? When you integrate them, their surface brightness over their area, you get something like this. But the surface brightness is the same. So these two terms will actually fall out, and you are left with the ratio of their surface areas, or if you do it differentially, it's the theta d theta and beta d beta. And then the magnification is just the ratio of how much does a small bit of a surface of a source here change when you lens it forward. I know this is not an easy concept to grasp, but I think this is something that we need to think about a bit more. I'll just briefly explain where we go from here. So this is the magnification, and it basically, what it does, it boosts the flux of the source you observe by this factor mu. So your galaxy gets, if your mu is 10, your galaxy gets 10 times brighter. And the resolution, because this is a ratio of solid angles, which is, think of it as a square. We have a square here, or a circle. We have a circle here, maps onto a circle here. The ratio of the areas is mu. The ratio of the resolution you have, the radius, is square root of mu. But the point here, when you are going to do observational astronomy at any point with lenses, is that the galaxy is boosted by a factor, the flux is boosted by a factor of mu. Your signal gets, let's say, 10 times brighter. And let's say I'm observing I want to observe a spectral line in a high redshift source, and this is what we'll be doing on Wednesday a lot. And I want to detect it, let's say, 5 sigma significance. So if the galaxy is not lens, I need, let's say, 1 hour of time to get this line at 5 sigma significance. When you do these signal-to-noise ratios, you need to know that your signal stays the same no matter how long you integrate, because the source is the same, but the noise goes down as the integration time square root of that. This is just the Gaussian noise. But when you think about the signal-to-noise ratio, that means that the signal-to-noise ratio, if you have lensing, goes up as mu, but your on-source time goes down as mu square. So if your galaxy is magnified by a factor of 2, you need a quarter of observing time to detect some line in it. Is it magnified by a factor of 10? You save a factor of 100. And like, factor of 10 is not too crazy. Like, I'm now running proposals where we have galaxies with magnifications of 20. So something that you would normally use, we are doing this with the very large telescopes, observations that it would take weeks to do on a single galaxy, we can do in a few hours. It's crazy. This is just day 3. I'll explain. And if I can take a bit more time for a couple slides. Okay. I would like to talk about magnification and the point mass again. And this is a derivation that was supposed to happen this afternoon. You were supposed to do it. So you'll be most likely doing it tomorrow afternoon. But basically, you have this expression for magnification. And for a point mass, you have this pretty simple equation. So basically, what you can do is, you can calculate these things. I mean, you can take the derivative of this with respect to, you can express theta in terms of beta to the ratio. You can do that. You can do the derivative. You can do that. If you do a bit more fancy algebra, not actually that fancy, is you get something like this. So your mu of a given image, and remember, with the point-like mass, you have always 2 images. Yes. It's 1 minus the Einstein radius versus the theta of your given image. So for the lens, is it gone again? Okay, with lens you have this angle going up. You have 1 image above the line, 1 image below the line, the axis of symmetry. So you have to take these distances here. And just to give you a brief overview of how this looks like, so now I expressed theta in terms of beta and Einstein radius. And so you have 2 images. I'll call them positive and negative, and you'll see why in 20 seconds. So take the image that has the positive sign here. That's the positive image. Okay, so it took 3 seconds. So you have always and you start with the source perfectly aligned with your lens. And then we move it away from the center of symmetry. So you start perfectly aligned, then source moves away. So at the beginning, when you do this equation, source is at 0, then you have 1 image at plus Einstein radius, 1 image at minus Einstein radius. And as you go further away from the source, 1 image, as you move the source away from the axis of symmetry, 1 image gets further and further away, and the other one gets closer and closer to your lens. I'll just try to demonstrate that. See here? There are these 2 images. One is very close to the lens, one is further away. The same here. Oh, I'm going to burn myself. And then you can consider how are they magnified. So this is your formula for the magnification. This is your formula for the distance between the lens, the distance between the lens center and the image position. So just plug it here, and I did these plots just to show you. So the image that's further away from the lens, the positive image, has if you go, if it's perfectly centered behind the lens, you have Einstein radius, you have this ring with basically infinite amount of points. This shoots up to infinity and then goes down to some value that approaches 1 at very long radii, because very far away from the lens, you don't care about the lensing anymore. And then you have this negative image where you have the minus sign here, and it has negative magnification, what the hell? Also very large, and then it goes down to 0, so it gets closer and closer to the lens. The magnification is 0, which makes sense, right? If your source is super far from the lens, all the flux from the source is over here, and there is no reason why there should be something bright close to the lens. If you add this to magnification as an absolute value, and you take a case where you have a lens and a source, and the source does this. It moves behind your lens. Very far away, the total magnification is 1. I mean, that's kind of expected. Then it goes up. Then it diverges, and my plotting routine didn't want to plot that, but it would go up to infinity, and then goes down again. As you go like this, does it really go to infinity? No. We saw before that when you have this perfect alignment where everything is point-like, your ray optics approximation fails, and you need to use diffraction, and then it actually doesn't get to infinite values. And I'll skip the next. Okay. Do you still want to do a quiz and then wrap up, or what would you prefer? Okay. I didn't cancel quiz this time. But I would like to still bring these plots up. Yeah. So I would say just very briefly, I would reproduce these two plots. So basically, the function of your theta over beta over psi over theta does something like this. No. Whatever. And then when you consider your magnification, we go to something like this. And now I'll do last 2 quiz questions and last 2 slides, and we are done for today. So we are now considering having a point interesting order of questions, but so forget for a moment about those plots and just try thinking in terms of symmetry. Which of these lensing configuration is possible? Now you have to think in terms of orientation of the images. So it's either A, B, C, or D. Are these, You don't know how the background source looks like. I won't tell you that. It's a rabbit. But think which of these, in terms of flipping, is possible. Oh. Now I still need to check whether I marked the right answer. So the most answers went to B. That's actually very good thinking. So you have circular symmetry. So basically, if you take if I have my lens, I have a source over here. I have one image over here, one image down here. Let me draw this. I have a big circle in the sky. This is the center of the lens. I have one source here. So there's an image here and an image here. if I extend this source to this direction, this image by circular symmetry will start moving up here. Okay, I'm very good at better drawing, and this will move around here. So you're totally right that if you consider a rabbit, you know, head is here, they do like a flipped side, so they can't be going in for a kiss. This is not possible. And they can't be jumping in the same direction because now both of their heads are pointing downwards. But think now about what happens when I have a source over here. By circular symmetry. Sorry. I have a source over here, yes. So, compared to this image, this will go over here, right? I think we can agree on that reasonably well. And also, you move further away from here, and remember that the difference between the positions of the two images is roughly 2 Einstein radii. It will be in here. Because otherwise, what it would mean, as you move your source further away from the lens, you would have an image, you know, you want, if I make my source over here, I expect one image to be somewhere over here because it's somewhat lensed, but not too much. But I don't expect the second image to be very far away. It actually needs to get closer and closer to the lens. So the ears of the rabbits, what happens in the radial, hang on. They are flipped in the they are flipped in this direction, but you can't flip them along this way. And that's the point, that's the last point I'll make today. That's the explanation for negative magnifications. It doesn't mean that your source becomes negative. It's a nice way of saying that your image will be flipped. So if this rabbit is a positive image, this one is the negative image. There is a different image parity, and all what it only means is the sign here is reversing. Because you went from a, let me see, so you have beta pointing in this direction. The same orientation is preserved here, so your theta increases in the same direction as beta. These are two-dimensional vectors, but here, theta is flipped. So as your beta goes down, your theta goes up in the vector space. And to make sure that I'm not bullshitting you, here is a nice demonstration of that in a real lens. So these are radio observations of a lensed quasar, and you see they're almost like a yin and yang. This thing, okay, you know, this thing comes up here, this blob goes down here. They are flipped in the tangential direction. And that's where I will leave you with for today, because I'm 15 minutes over time. Thank you very much for attending. Thank you very much for making it. You'll be receiving an email, I believe. We have your emails with the background material and the slides from today. And if you want to, I can send 1 or 2 short exercises. This is not a homework. You can do it in your own time, just to make sure that, you know, if you want to work something after day 1, there will be some short stuff for you. And I believe that's it for today. Thank you very much.